Those are the physical properties I'd like to know. When I start seeing vapor pressures, now this is the world according to Doug. This is not based on any scientific fact. It comes from 29 years of experience in hazardous materials. When I start seeing vapor pressures greater than 100 millimeters of mercury, you have my full and immediate attention. Because that's telling me that stuff is going to become airborne very quickly. Especially you put that 100 millimeter of mercury vapor pressure liquid on the floor inside an enclosed building, now you really got my attention. Now that's not to say that things with lower vapor pressures can't be really hazardous to us, because if we look at toxicity, which is where we're going, if you could only figure out one or two things about the toxicity of a material, what would you like to know in order to analyze the risk to your personnel and the public? IDLH, and one other. Route of exposure. Speak up, don't be afraid. Those are the two things I'd really like to know about a material to determine hazards. How does it get into the body and how toxic is it? Well, if I got something with a vapor pressure of 20 millimeters of mercury, which is below 100, but its IDLH is 2 parts per million, then that 100 vapor pressure really doesn't mean anything, because I got something that's extremely toxic, right? So you got to take vapor pressure in comparison to IDLH. Now, if it's got vapor pressure of 20 millimeters of mercury and the IDLH is 1,500 parts per million, I'm probably doing all right. But that IDLH of 100, boy, when I hit that IDLH of 100, for me personally, for Doug Wolf personally, I'm very, very concerned. And God forbid that the IDLH be below 100 and the vapor pressure be above 100. Then the hair on the back of my neck is standing up, and we are definitely going level A. Because we're going to have a lot of vapors, and and a route of exposure other than just inhalation. I'm definitely concerned about it. Good with that? From flammability standpoint, what would you like to know? What is the number one thing you'd like to know about flammability?
Is it flammable?
Okay.
LEL?
Give me one more.
Flashpoint.
Flashpoint.
Flash.
And flashpoint's most important, and flashpoint is directly related to vapor pressure. The higher the vapor pressure, the lower the flashpoint. As vapor pressure increases, flashpoint, or the temperature at which the liquid will evolve sufficient vapors and air to form an ignitable mixture, decreases. So the higher the flashpoint, the higher the vapor pressure, the lower the flashpoint. Then I want to know range. LEL to UEL. If I know it's flammable or combustible, do I really need to know range?
Just the LEL.
What's going to tell me whether or not I'm getting into trouble? If I send a crew down range, what's going to tell me whether or not I'm getting in trouble? Your combustible gas indicator is going to tell you that. Do I have to know the flammable range? No. Is it good to know? Yeah, if we have it available. And the wider the flammable range, the greater the risk. And as we add oxygen to a molecule, like we saw in ethers and peroxides and alcohols and some of the carbonyl group, as we add oxygen to that molecule, we begin to widen that flammable range.
Would you worry about not knowing the conversion factors and all that other stuff with that flammable range, because you may be within that range if you don't have the correct conversion factor, right?
With a few rare exceptions, I would. The reason we are making a go no go decision at 10% of the LEL is to leave enough safety factor in there so that we aren't too far away from that. Now there are something like ammonia gas. You have to multiply your meter reading typically by 2, which if you hit 10% of the LEL, you're actually at 20% of the LEL. So there is enough of a safety factor if you use 10% of an LEL that typically you still aren't hitting the lower explosive limit. But definitely, if we know what the material is, we do want to know what the conversion factor is for that instrument so that we can make a more accurate decision as to whether we're hitting 10% of the LEL in a confined or an enclosed space, or how many use 20 or 25% outside? Anybody here? Some, I mean, Coast Guard and EPA use 20 to 25% outside open air environment, but they use 10% in confined space and enclosed buildings. It's up to you and your organizational policy. The only mandated one legally is 10% LEL in a confined space. Okay? But yeah, if you're going 10% of the LEL and you don't have a conversion factor, you don't know what the material is yet, you're probably still going to be in a 4-to-1 or 5-to-1 safety margin. Okay? Go with that? What about from a reactivity standpoint? We'd like to know if it's water reactive. We'd like to know if it's an oxidizer. We'd really like to know if fluorine's in there. What's the most reactive compound or element on the periodic table? What's the most reactive element? Fluorine. Very, very small compact molecule?
You could probably say the same for fluorine.
Really? You think?
Opposite.
Most reactive metal is phosphine. Most reactive non-metal is fluorine. Think about what Steve said yesterday about as we add energy levels, what happens to the radius of the atom? It gets bigger and bigger and bigger, right? That means those positively charged molecule or positively charged protons in the middle of that atom cannot control those outer electrons as well. So they're out there, those valent, the group 1 electron is hanging out there, and that positively charged proton in the nucleus can't hold it in real well. That's why those group 1 elements are so willing to give up that 1 electron. Because we've just added another energy ring, right? We've filled the order, we've come back and added another energy ring, which makes the radius of the atom bigger. But now it's only got 1 electron hanging out here, and that positively charged proton in the nucleus can't hold it that well, and it will tend to give it off. Whereas over here, as we gather more and more electrons and protons in the nucleus as we move from left to right, that nucleus starts getting bigger and bigger and bigger and really starts pulling those electrons in real tight. So as you move, it's easier to show it this way. Here's our periodic table, somewhat bastardized. As we move from left to right, the radius of the atom gets tighter. As you move from left to right in the same row, the radius of the atom gets tighter, which means they exert greater control over their electrons, and they want to take electrons more. As you move from top to bottom, you're adding another energy shell. What's happening to the radius? It's getting bigger and bigger. So down here you got that big one, and in particular in this first row, with the exception of hydrogen, in the alkali metals, this electron's way out here, and that nucleus in here with all of its positive protons can't hold on to it so well, and it tends to give it away. That's why they're so water reactive. These over here, that nucleus is close to that outer shell because it's pulling it in tighter and tighter, and these over here steal electrons very easily. That's why these won't give up electrons. They'll take electrons from over here, but they won't take them from themselves. All they can do is what? Share, right? And the one that is the tightest radius element in the non-metals is going to be what?
Fluorine.
Fluorine, because it's only got 2 shells, and it's got 7 electrons. All at once is 1 more. So the most reactive non-metal is fluorine, and the most reactive metal is franknium. Cool stuff? That's why we are very concerned when fluorine is involved in a molecule. Because fluorine is extremely reactive, and we're going to come up against some acids. Anybody familiar with hydrofluoric acid? Or hydrofluorosilicic acid? We'll talk about that when we talk about industrial materials. So we'd like to know if they're water reactive. We'd like to know if they're air reactive. Pyrophoric. These elements here that border that metal, non-metal line have an ability to go either way. They're actually called metalloids because they can either act like a metal or they can act like a non-metal. But when you bond them with organics, you make things like silane. Anybody here got an electroplate? I'm sure you've got silane on Los Alamos. Silane is one of those pyrophoric gases that in contact with air will spontaneously combust. So we want to know if it's air reactive, water reactive, oxidizer would be really nice to know. How about pH? We'd like to know. That really is all the information you need to know about a material in order to make a basic initial hazard analysis of a product. To make those decisions in the first 15 minutes, 20 minutes, after you've used your emergency response guidebook. Don't ever forget the basics. Use the emergency response guidebook, get the ball rolling in the right direction, then go to the NIOSH pocket guide and start finding out this information. And if you like, I got a little worksheet I'll give you that I'll put it on the shared drive that I got. It's a little worksheet that it's a rapid hazard analysis. Now, what do we do after we make decisions based on that? We hit the books. We go to at least 3 sources and start finding out more and more and more. But this will get you moving in the right direction. One other hazard we got to think about. Radioactivity. Is it radioactive? And how does it decay? Is it an alpha only decay? Is it a beta only decay? And after it decays, will it give off gamma radiation? And most of them, when they decay, man-made isotopes or concentrated isotopes, the vast majority of them, the decay mode is alpha or beta. And what happens is when it throws off that alpha particle or beta particle, there's excess energy left in that nucleus, and that nucleus shunts off that excess energy as a photon of energy, and that is called gamma. So gamma is not actually a decay mode, it is a result of decay, just to be technically correct. Right? What's going to hurt us? Gamma, right? Alpha is only going to hurt us if we ingest or inhale the source material that's giving off the alpha or the gamma. Think about, oh geez, I don't know if you all were in the service then or not. There, probably 15 years ago, there was a guy in Great Britain that was assassinated by former KGB by putting polonium-210 on his salad in a restaurant. Polonium-210 is a alpha-only emitter. It emits only alpha. There's no gamma being given off, so it decays alpha. They put it on a salad, he ate it. Well, it started ionizing all the tissue of his gastrointestinal tract, and guess what happens when you do that? Yeah, you die. A couple days later, he died of electrolyte imbalances, fluid shifts, damage to the gastrointestinal tract. Why'd they use polonium-210? Because you can stick it in a plastic bag, put it in your pocket, and fly from wherever you did over in the former Soviet area to Great Britain, you sprinkle it on the person's food without anybody being able to detect it. Right? Alpha is not going to go anywhere, right? Yeah. Better living through chemistry, right? Or in this case, physics.